So
hopefully, yes.
So we're very happy to see you and to hear you as well.
Yeah, thank you. Thank you for invitation, and thank you. I'm sorry that I cannot be there personally, but due to other obligation, I cannot move from my laboratory. But I'm very happy to share with you some of our recent achievement and still ongoing idea that are under development in my laboratory. So let's see. This is the agenda for today, so I will try to underline why we need to do more with less, and even in a faster way. That's the common struggle that in the clinical microbiology laboratory we have, I believe, all over Europe, but in Italy is particularly true. And I will take some time to discuss about the 16S, rRNA sequencing, and something more. I would like to report on the use of MALDI-TOF, mass spectrometry, and then I will include some newer technology that have been developed in my laboratory and that are nowadays almost available on the routine market possibility, like the infrared spectrometry and the very simple and easy to use lab-on-chip that we developed together with LPAX. So why we do need to go for more? Because the quality of our service needs to be higher and higher, and this is even more challenging in this current age in which we are, of course, experiencing, at least in Italy, but again, I believe all over Europe, a declining reimbursement ratio. So we do need to do more with less money. And another issue that we have to face with is the consolidation of medical care into large hospital system and networks. That means that, like for my laboratory, most of the larger laboratory for microbiology needs to serve a network of hospitals. That means at the very end, an increasing number of specimens received by laboratories and specimens that are collected at satellite location. So this brings to us the new concept of unique microbiology laboratory that perform testing for multiple healthcare facility and physician office as well. At the very end, if we want to keep on pace and provide the response, the answer to the clinical prescription that we get, it's mandatory for us to go for the highest possible level of automation in order to keep the level of our performance adequate to the clinical needs. So at the very end, I also believe that the challenge for the new microbiology laboratory will be to improve efficiency. In other words, we need to do more with less. We need to have a better turnaround time for our results, especially as we have just heard, in severe patients. We do need to be time effective. We do need to report our results in the shortest possible way. And we, at the very end, need to go for a better integration of the standard, the classical bacteriology, with other technologies such as mass spectrometry and molecular diagnostic. So in the last 20 years, clinical microbiology has witnessed a major development that started again 20 years ago with pre-analytical steps, a new collection device. It was when we introduced the so-called liquid-based microbiology that brought all of the sampling in a liquid phase. That was a huge improvement because at that time we were able to think about automation in the pre-analytical step also in bacteriology. Some 10 years later, we have the possibility to include microbiology automation and imaging based on artificial intelligence. That was very impacting on our routine work because that was the first steps that allowed to reduce the request for specialized personnel and started to reduce also the incubation time. Some 5 years ago, it became more and more routinely available the possibility to have rapid system for bacterial identification, and I will discuss something about this. Well, the idea that the rapid determination of the identity of individual bacteria could be based on sequencing and identification of the 16S ribosomal rRNA is not really that recent, because it started in the mid 80s of the last century with this paper that appeared in 1985. This is a very complicated picture that report how is the variable region of the 16S ribosomal RNA gene in relationship one to another in the total gene. And you see here that there are more than 9 different regions that can be very easily used to classify and to, at the very end, identify the bacteria. In this picture, you see how many millions of sequences are already available nowadays in the international databases for the identification of the 9 different V1 to V9 variable region of E. coli, that is, of course, one of the most widely studied bacteria. And you see that, for example, for region V3 and region V4, we have more than 2 million deposited sequences. That means, at the very end, that this is a very robust technology. It's very hard to imagine that if you work with the PCR-based sequencing for these 2 regions, you cannot get correctly the E. coli. Of course, E. coli is one of the most widely studied bacterium, but if you go at the international database, you will see that all of the most relevant bacteria in the human infectious disease are reporting thousands of different sequences. That at the very end, again, means that this technology based on the 16S RNA identification is a very robust one. And this is a paper that we published some year ago before the COVID pandemic that was an evaluation of a rapid bloodstream, rapid diagnosis of bloodstream infection in severely ill patients coming from the ERs. And that was based on a broad range PCR mass spectrometry combination technology. That was really a good paper, a nice experience. But again, if you look at these, the system was called Iridica, that is no more available on the market because a very complex system. So they decided to withdraw due to major issue in the I would say commercialization of the system itself. But it was capable to identify more than 800 different fungi and bacteria species, starting from primary blood sample taken from patients suffering from acute suspicion of sepsis. And as we just heard in the previous lecture, the issue when you work with such a huge and powerful system is that it's not simple to take a complete agreement in between the molecular system and the standard blood culture, as you see here. Just to provide you some ideas, we had some unmatching results between the PCR ESI MS, and the organism identified by blood culture. In this case, just to give you some example, we identified the 16S RNA gene from a Klebsiella oxytica, but the blood culture provided the presence of a Proteus mirabilis. And so who's really the real agent of this infection? And the only way to solve this issue was to go for the clinical record of the patient, go back to the clinical record of the patient, and to find out if there were some additional information. In this example, we detected the same Proteus mirabilis from urine culture in the same collection in the same days. So again, this is to state that we cannot really trust completely the molecular test performed on the primary blood sample. because it's indeed, at least in this particular situation, a very powerful system, but probably not enough evaluated and assessed under the clinical point of view. But again, genomic is a very powerful system and technology that can be used for the identification of bacteria, as you see here in these graph derived from the number of publications found in PubMed up to 2017. What is right now on the edge of being in our routine work? Indeed, next generation sequencing is playing, especially after the COVID-19 pandemic, is playing a very relevant role in clinical microbiology. We have three major possibilities so far for applying the next generation whole genome sequencing or metagenomic approach in the clinical microbiology in order to enhance our capability to identify faster and more accurately bacteria. The first approach is to start from pure culture in which we grow a known organism. And this is, I would say, not so useful because we have a lot of other very affordable techniques that can be used for the identification of bacteria from colonies. But if we move to the second approach, that is taking into consideration a clinical specimen that is composed by normal host microbiota and possible pathogens, that means we are working with pathogens that are mixed with the normal flora. Is getting back. We need to extract and purify the DNA. We can enrich for selection of the 16S RNA, for example. We can prepare a library and we can go for NGS sequencing, and then we can have a huge set of 16S RNA gene that enter into the profile analysis, so that we can completely identify all of the bacteria that are playing a role in dispatchment. The third approach is just to go for a more wide approach that is considering all of the genes and providing additional information in the NGS. Of course, the advantages and disadvantages of the NGS sequencing is still under debate. In general, I would say that the application in whole genome sequencing from primary clinical specimen has a lot of advantages, but also many disadvantages as enlisted in this table. Among the more relevant advantages is the general identification and typing, the prediction of antimicrobial resistance profile quite accurately nowadays, because we have, as it was shown for the 16S RNA genes, we have also a huge library available that include most of the antimicrobial resistant related genes. We can, by using the whole genome sequencing by NGS, we can discover novel resistant mechanism. We can study virulence factor. We can provide entire genome and plasmid sequence that is indeed very useful in order to differentiate different microorganisms. And we can also, at the very, very end, allow for single nucleotide polymorphism and mutational analysis that looks very promising as a technique that can establish the identity of different isolate, for example, coming from the same hospital-acquired infection outbreak in a single hospital. This is the only technique so far that allow us to state, okay, this germ has been identified in patient A and move it to patient B and to patient C. So that will be a very powerful system, and it actually is already a very powerful system that can allow us to state which is the path followed by bacteria inside an outbreak of hospital-acquired infection. But on the other hand, we have also disadvantages because bacterial whole genome require growth and isolation of colony. This is not a big issue, but in any way, it's necessary to go for starting from pure colony. It cannot accurately predict susceptibility, and some predictions are not so reliable for certain mechanisms of resistance, especially when the mechanisms of resistance are not completely connected to defined genes, and large depth of coverage need across entire genome. That means at the very end, a higher sequencing cost, and due to these requirements for deep sequencing that is not so easy to be achieved, but is becoming more and more achievable day after day. But more realistically, what we can do today is bacterial identification by mass spectrometry. It is becoming, I would say, a routine possibility for the largest number of clinical microbiology laboratory. Matrix-assisted laser disorganization, ionization, this huge and very complex definition is nowadays more and more famous as Malditov MS. It's based on mass spectrometries. I would say that this introduction is probably one of the most significant advances in clinical microbiology, at least in bacteriology so far, in 30 years, because it provides rapid and cost-effective identification of bacteria directly from isolated colonies and also from positive blood culture based on a spectrum of proteins. Proteins biomarkers are highly expressed protein responsible for housekeeping functions such as, again, the 16S RNA ribosomal protein pops up again, and for transcription and translation factor protein. So at the very end is fast, is ameliorating our workflow, is not really expensive, but is not perfect. And we will see why it's not perfect. This cartoon very simply and possibly not completely depict what is the normal workflow in case of patients suffering for suspected sepsis in the laboratory. So the patient is sitting here, the samples are collected, the samples are processed based on culture-based isolation that at the very end, in the best possible option, takes 24 hours, but very commonly takes up to 5 days. So if you can work directly on sample, we can skip over this step, and at the very end this means that we can have a faster identification that could be in between 5 minutes and 48 hours. So what we have presently available is a culture-based, molecular-based, and mass spectrometry performed on positive blood culture. It's emerging the possibility to go for molecular and imaging-based, as we just did in the previous lecture, by using also molecular method and in particular by working by sequencing technology. In the future, there will be electronic noise and other, I would say science fiction related technology that are recently getting into the landscape of clinical microbiology. So it's really realistic that in the near future, our antimicrobial susceptibility testing could be really made available to the clinician in order to set up a pathogen-targeted therapy within 2 to 4 hours. And of course, the Malditov holds a very wide possibility to be applied on primary samples, but at the very end, this is very complicated, and it probably is not impacting so deeply the management of our patient. What is realistically done each day in most of the laboratory is to apply Malditov technology directly on positive blood culture. And this is really realistically, it's a routine that can be done. We still have some issue that should be faced and solved on a local situation, and the major issue are removal of human proteins, because in the blood we have a lot of protein that can interfere with the acquisition of the bacterial protein spectrum. We need to have some extraction protocol we need to have at least a bacterial concentration of about 1 times 10 to the 7 per ml, but this is easily achievable in a positive blood culture. This is the lowest concentration of bacteria that usually we have in a positive blood culture. And what is the major issue? That is that this system works not perfectly whenever we have a polymicrobial grow inside the blood culture. And of course, getting back to very classical microbiology, before performing this technology, we need to go for a gram staining and look if we have under the microscope the idea that more than one bacterium can sit inside the culture. Which are the advantages of MALDI-TOF in this respect? The major advantage is the ability to identify an increasing number of microorganisms. We need to work only on single colony. The turnaround time of MALDI-TOF identification is less than 5 minutes. It's very easy to be performed in all of the laboratory. It's requiring a very minimal training. It's extremely, oh, come on, I need to go back. Is really cost effective. The reproducibility is very high. The database can be expanded locally. It's indeed a green technology because we have no plasticware involved within that. Getting to the issue of limitation of this technology, of course, the initial cost of the instrument could be impacting on the laboratory budget. We need to have a minimal amount of cellular material. It cannot routinely be used on direct clinical sample. In selected cases of closely related organisms such as E. coli and Shigella or Streptococcus methiceralis and Streptococcus pneumonia, the distinction is not all the time available. If you go for this kind of technology in the routine workflow, there is the fear that some of the traditional microbiology skill will be lost in a few years, and it's indeed an issue. In general, the availability of antimicrobial susceptibility is not so widely achievable. The technology that can provide the information about the production of carbaphenemases, but not for all the antimicrobial susceptibility issue is possible. In general, is not usable with polymicrobial culture because the spectra are overlapping one to another, and so the interpretation of the acquired data is not that easy. So despite this limitation, the direct from specimen identification has been attempting on positive blood culture and urine specimen, and it's nowadays in routine. So what we have available right now, in summary, is taking a blood culture for a suspected patient with sepsis, and we can either go for MALDI-TOF identification, Herdy subculture, or classical subculture. But if we work in this way, we can try to go for an identification that stay within 12 from 18 hours. Whereas if we go for the classical subculture methodology, it takes up to 24 or 48 hours. So, of course, all of the possible improvement in this area, and nowadays we have a lot of different possibilities, are impacting on the management of our patient. So, and now I'm coming to something that is just started a few years ago in my laboratory. We started to collaborate with a company that was developing this new spectroscopy. It's an infrared spectroscopy that has a major difference in respect to MALDI-TOF. MALDI-TOF only acquired protein-related spectra, while the infrared technology acquired a more complete set of possible spectrum for any single bacterial cells that include protein, nucleic acid, lipid, and carbohydrate. So these spectra are much more complicated, but provide a lot of different and more complete information about the identification. This is the already available machine. It's very simple to be performed. You just need to go for a colony, single colony, just tweak the colony over this acquisition area, and then in 1 minute you get identification without any additional preparation. So in practice, this attenuated total reflection free transformed infrared, which is behind the acronym ATR FTIR, is a vibrational spectroscopy that provides with a fingerprinting of each single species, bacterial species. The spectral acquisition is very fast, the data processing is very fast, and then you need the software that can be used for the analysis of the spectral component, and then the software provides a classification of all of the spectra you are acquiring, and you get the final ID within no more than 2 minutes. So far, the database is less including than the multitude of databases, but you can very easily identify yeast, such as Candida, different species, gram-negative bacteria, including all of these species and subspecies, and gram-positive bacteria that works quite easily. So the database reference has been now including more than 15,000 spectra, and so it's increasing day after day with this different methodology. That means that all of the identified species have been grown in different media with different colonies, and at least 275 spectra for each species is required for the inclusion of the, say, medium average spectra for the identification. So the normal workflow that we are working on is requiring 1 or 5 colonies or pellet,